Hi, I'm Kai. Now I'm going to do the question 7 of homework 7 for probability and stochastic processes. The question 7, we have the function z of t is equal to n1 of t times cosine omega c t plus theta and plus n2 of t times sine omega c plus theta. The question 8, we need to find the expected value of z of t. So the expected value e of z of t is equal to e of m1 of t times cosine plus n2 of t times sine. So the expected value of the sum is equal to the sum of the expected values. So we can rewind this term as their sum of their expected values. So for the first term, we note the m1 of t and theta are independent, so we can rewind this term as the product of their expected values. So for the second term, it is the same. We can rewind it as the product of their expected values, and because the n2 of t and theta are independent. So, and we also note the n1 of t and n2 of t are y-sense stationary. So we can let the expected value of n1 of t equal to eta1, and eta1 is a constant, and we also let the expected value of n2 of t equal to eta2, and eta2 is also a constant. So we can rewind the expected value e of z of t as the eta1 times the expected value of cosine and plus eta2 times the expected value of sine. So for the first expected value, we note by the definition, and it is equal to the integral cosine omega c t plus theta times the density function of theta d theta. And for the second term, the expected value is equal to the integral of sine omega c t plus theta times the density function of theta d theta. And we know the theta is uniformly distributed in 0 to pi. So the density function of theta is 1 over 2 pi. When theta is between 0 and 2 pi. So we can rewind the expected value as n1 times the integral. The lower bound is 0 and the upper bound is 2 pi cosine times 1 over 2 pi times d theta. And the second term is eta2 times the integral. The lower bound is 0 and the upper bound is 2 pi, and sine times 1 over 2 pi times theta. We note for the cosine function and the sine function, if the lower bound is 0 and the upper bound is 2 pi, and the result of the integral will be 0. So the first term will be eta1 times 0, and the second term is eta2 times 0, and the final result is 0. The problem B, we need to find the autocorrelation RZ of T1, T2. So by the definition, RZ of T1, T2 is the expected value E of Z of T1 times Z of T2. So the Z of T1 is N1 of T1 cosine plus N2 of T1 times sine, and the Z of T2 is N1 of T2 times cosine plus N2 of T2 times sine. So if we and this term times this term, we can have the first term, and this term times this term, we have the second term, and this term times this term, we have the third term, and this term times this term, we can have the fourth term. So we need to calculate the four terms, and then we add them together, and then we can have our autocorrelation. So for the first term, E of N1 T1 cosine times N1 of T2 times cosine. Again, we know the N1 and theta are independent, so we can take out the expected value N1 of T1 times N1 of T2. This term, if we left T1 minus T2 is equal to tau, so it will be Rn1 of tau. So for the term inside, we can use the product to term formula for cosine. So the formula is cosine alpha times cosine beta is equal to 1/2 times cosine alpha minus beta plus cosine alpha plus beta. So so this term will be equal to so this term alpha plus beta will be equal to omega c times T1 plus T2 times 2 times theta, and alpha minus beta, the result will be cosine omega c tau. So we can use the method in the problem 8. So this expected value will be equal to the integral. Lower bound is 0. The upper bound is 2 pi cosine plus cosine omega c tau. So it's the same. This term is 0, and we still have this term. So the final result will be 1/2 times r of n1 of tau times cosine omega c tau. So for the second term, we can use the same method. We take the expected value of n1 of t1 and n2 of t2 out, and for the term inside, we use the product to sum formula, and it will equal to 1/2 times the integral lower bound is 0, upper bound is 2 pi sine omega c of t1 plus t2 plus 2 times theta times the density function theta minus sine omega c tau. So for the third term, we use the same method, and the result will be eta 1 times eta 2 times 1/2 times the integral sine times the density function theta plus sine omega c tau. So for the fourth term, it is the same. We take n2 of t1 and n2 of t2 outside, and it will be the r of n2 of tau. And for the inside term, we use the product to sum formula, and this term will be equal to 0, and we still have this term cosine omega c tau. So the final result will be 1/2 Rn2 of tau times cosine omega c tau. And finally, the autocorrelation Rz of t1, t2 is equal to the sum of these four terms, and we add them together, and finally we will have 1/2 times Rn1 of tau plus Rn2 of tau times cosine omega c tau. It is equal to Rz of tau. So for the problem 8, we note the E of z of t is 0, is a constant, and from the problem B, we note the autocorrelation Rz of t1, t2 depends on tau only, so z of t is a y-sense stationary. So the problem C, we need to find Rz of 0. So Rz of 0 is equal to 1/2 times Rn1 of 0 plus Rn2 of 0 times cosine 0. So the final result is 1/2 times E of n1 of t squared plus E of n2 of t squared.